Good afternoon, everyone, and welcome back to AP Physics 2. We are one day closer to exam time as we start electrostatics, topic number 3. Today, we're starting with the idea of electric charge, the idea of conservation of electric charge, and how things become charged, either by friction or conduction or induction. As always, we're going to run through the agenda first. We'll start with a lesson overview and talk through what we'll be doing in today's lesson, and then we'll do our daily warm-up. We'll pick up where we left off yesterday with the last question from thermodynamics, and then segue into some work for today. We'll outline what you need to know to be successful on an electrostatics question, should you have one on the AP exam. And then we'll walk through some guided practice, some released questions from the College Board that'll point you in the right direction as you prepare for this test. We'll do a debrief and summary. You can make sure that you learned everything that you planned on learning. And then finally, we'll leave you with some AP practice questions for tomorrow. So I am Joe Mancino from Glastonbury High School in lovely Glastonbury, Connecticut.
And I'm Brendan Eaton from Reedy High School in Frisco, Texas. Now let's go ahead and take a look really quick of our overview of the rest of the courses that we have available for you. We've already taken care of fluids and thermo. Today we are beginning electrostatics. So where you see the arrow is the first of 4 lessons on electrostatics. And then we'll dive into circuits and magnetism to finish out your review for this AP exam. So make sure you have taken some time to look at that schedule and know which lessons you definitely don't want to miss. So as far as today's lesson is concerned, we're going to begin by talking about electric charge, specifically charges inside of the atom. What is an elementary charge, and how do insulators and conductors behave dealing with charges?
And then we'll talk about the law of conservation of charge, the idea that the total amount of charge before some kind of charging event is equal to the total amount of charge after some kind of charging event. As with energy, it's your job to follow the charges and keep track of where it goes.
All right, we'll also review the types of charges, specifically friction, induction, and conduction, and how those interact between multiple objects and with single objects.
Here are the things we think you already know going into this lesson. I think that you know that there's positive charge and negative charge, and there are some things that don't have a net charge. You might not know how and why they become charged. We'll discuss that today. I think that you know that in a metal material, there's a sea of electrons. The way that metal atoms are bonded together, electrons can more easily flow.
And by the end of the lesson today, we hope that you can determine the charge of objects in various scenarios and understand the different types of charging and how they are actually happening on the microscopic scale.
And the skills that we'll be working on today are explaining things based on evidence produced during scientific practices. So explaining how the behavior of certain materials gives evidence of the two-charge model. We'll be making claims and predictions about natural phenomenon, and we'll be connecting concepts in and across domains. So gluing topics together across domains. We're going to open with the question from last class. So last class, we presented you with this problem. There are 3 samples of an ideal gas: sample X, sample Y, and sample Z. X is the hottest, Y has a temperature somewhere in the middle, and Z is the coolest of them. There's a graph showing the speed distribution for sample Y. That is a graph showing the number of molecules that are going any particular speed. The speeds are there along the x-axis. So what this line shows you is that most of the molecules are going that at or near that average speed, and there are some going a little faster and some going a little slower. Well, what would that look like if a gas with the same number of molecules had a higher temperature? Well, there's two clues in there. The higher temperature means that the spike in that graph, the maximum number in that distribution, is going to be shifted rightwards along the x-axis. It's going to be at a higher average speed, but also that each gas contains the same number of particles. That means that the area under that curve for another line would be the same as the area under the curve for sample Y. So here's what I drew for sample X. It is a curve with a peak that is shifted right and also a curve that is shifted down. I thought that area looked about the same. Here's what I drew for sample Y, which is colder than, for sample Z, which is colder than sample Y. It has a higher spike, meaning that there are more particles going closer to that average speed. And also, the spike is shifted left along the x-axis at a colder temperature. All right, the samples are placed in thermal contact and insulated from their surroundings. They're just touching each other. And your job is to explain how energy flows between those samples. And yes, and discuss the changes in the kinetic energy in each of those materials. So in sample X and sample Y and sample Z. And your job was to identify a lot of things from this relationship. All we're told is that this ends up reaching some kind of thermal equilibrium with Y being hotter than when it started. So about block X or sample X. Sample X starts off hotter than sample Z, so the direction of spontaneous energy flow is from X into Z. The kinetic energy of X's molecules decreases because they're going slower, they cool off. Block Z is cooler than block X or block Y, so energy flows into block C from those other two. And the kinetic energy of block Z's molecules increases. Block Y is hotter than block Z. So initially energy flows from Y into Z and the kinetic energy of Y's molecules decreases. But we also know that Y ends up warmer. That was in the clues. So as Z gets hotter and hotter and hotter from its contact with X, Z begins to warm up Y. Eventually, the direction of heat flow changes as Z starts to warm up Y, and energy continues to flow until those samples are at the same temperature. The next question was about the net entropy of sample X as sample X gets cooler. As sample X gets cooler, its component molecules are vibrating with a slimmer variety of speeds, with a narrower subset of speeds. Its speed distribution graph would have a narrower spike. So we say the entropy of sample X is decreasing. More of its molecules are traveling closer to the average speed, but the entropy of the whole three sample system increases. Reaching thermal equilibrium is considered an irreversible process, which is the definition of a process that increases entropy. Left to its own devices, a system will approach thermal equilibrium and its higher entropy state. And then we left you with this question. 2 moles of an ideal gas are in a cylinder bound by a movable piston. It goes through this cycle. Here's some data about the cylinder, and your job was to calculate the net force. Now, from back in fluids, we said that force is pressure times area. And your job is to read the pressure off the graph, combine it with the area from the text, and say, yeah, that force is going to be about 500 newtons. Then the question said, well, can you calculate the temperature in state B? The text tells us there are 2 moles of gas. The PV diagram tells us the pressure and the volume at state B. We can combine all of that using the ideal gas law to get a temperature of about 600 Kelvin. Depending on how you round it, you got 601 or 602 or about 600. We had to talk about the change in the internal energy of the gas as it goes from state A to state B. The internal energy of the gas from state A to state B definitely goes up. We can say that at the same pressure, increasing the volume must have somehow we have increased the temperature of this gas. And then we have to calculate the energy added to the gas as it transitions from state A to B to state C. Well, the change in internal energy is 3/2 delta PV. I didn't show the intermediate step there, but I multiplied P times V in state A, and then multiplied P times V in state C. I found the difference between them, that's delta PV, and multiplied that by 3/2 to get 1500 joules. The follow-up question to that was to determine the change in kinetic energy, really the internal energy of the gas, as the gas is returned to state A. Well, if we know that the change in internal energy from A to C is plus 1500 joules, then the change in internal energy from C to A must be negative 1500 joules.
And here's what you need to know from today's lesson. So first off, with electric charge, we're going to explain the two-charge metal based on evidence. You need to be able to predict the sign and relative quantity of charge after a charging process. You should be able to predict the distribution of charge after a charging process. You should be able to explain charge separation by polarization and explain why it does not actually charge the object. Predict how charge will behave on insulators versus conductors, and be able to draw a representation of charges on an object. So we'll start talking about electric charge first. So you've already taken chemistry more than likely. You've already pretty much been through an entire Physics 2 course. So you know that every object is composed of atoms, and inside of those atoms, they contain electrons and protons. And electrons can carry a negative charge, and protons carry a positive charge. So going into elementary charge, this is a topic that kind of confuses students from time to time, so this is definitely worth the time on the review. The smallest amount of charge possible is the charge on an electron. And you may have this memorized, but it is available to you on the back side of your formula chart with all the rest of the constants. The charge on an electron is negative 1.6 times 10 to the negative 19th coulombs. But what would the charge of a proton be? You would say it's a positive 1.6 times 10 to the negative 19th. So the smallest unit of charge is 1.6 times 10 to the negative 19th coulombs. Now, any charged object has multiples of that elementary charge. Elementary means the simplest, smallest amount. So if there's an object with one extra electron, it has a charge of negative 1.6 times 10 to the negative 19th coulombs. If it has two excess electrons, it probably has a charge of negative 3.2 times 10 to the negative 19th coulombs. So we're going to work with this in just a second, but just know that when it takes 6.24 times 10 to the 18th electrons to make a whole coulomb of charge. Is it supposed to say one?
No, I changed the slide. It was supposed to say it takes 6.24 times 10 to the 18 electrons to make a whole coulomb of charge. I do want to bring everyone's attention to another smart thing that Mr. Eaton said. He said if you check your table of constants, your equation sheet, you'll see that these numbers are on there. But what happens if you left it in a binder or you left it in a locker and you might not be going back to school before the AP exam? Please go right ahead and download that now. The AP exam is less than 1 month from now. On May 13th, you'll probably wish that you had that table of information, that table of constants, and that table of equations. Now, you won't be expected to write out any equations, but you will be expected to understand the relationships that those equations describe. It will be a very useful tool for you to have, even though presumably you're not going to be crunching numbers on the AP test. It would be very useful to have that as one of your available resources.
Absolutely. And I think the easiest way to do that is just to Google AP Physics 2 formula chart, and it should be the first result. Click it, it's a PDF. All right, so let's practice a little bit with elementary charge. Let's say I've got these 5 objects, A through E, and the question is, which of these charges can this object not have? I actually kind of misspoke. Let's just assume there's an object and there's 5 different charges. Which one of those can the object not have? So since we just discussed elementary charge, and we know that the smallest unit of charge is the charge of an electron or a proton, which is 1.6 times 10 to the negative 19th coulombs, and all of these are in coulombs, what do you think you would do to figure out if that's a multiple of the charge of one single electron? Well, I gave an example earlier. I said, well, if there's 2 extra electrons, that's 3.2 times 10 to the negative 19th. That's just 1.6 times 2. So since you've got 5 different charges, what you need to do is go ahead and divide each one of those charges by the elementary charge, which is 1.6 times 10 to the negative 19th. The more you say it, the more you remember it. So if I do the work on this, the first one tells me I have 2 extra electrons, and the second one's going to be 2.8-ish. If you put that in the calculator, since 10 to the negative 19th cancels, you can just do 4.5 divided by 1.6, and you get about 2.8. If you take 8 divided by 1.6, this one typically tricks my students up. They think that it's not going to be divisible by 16 or 1.6, but 1.6 actually goes into that 5 times. So that would be 5 extra electrons or 5 fewer electrons than there are protons, depending on the sign of the charge. Now, what about 9.6? Does 1.6 go into 9.6? Or yeah, it does 6 times. And the last one is the elementary charge itself. So itself divided by itself gives you 1. So the answer to this is, which charge can the object not have? Well, that's not an even multiple of electrons. You can't have 2.8 electrons. You can only have 2 electrons or 3 electrons. There is no in between.
So a scrap of confetti, as you see in the image, has a charge of negative 20 microcoulombs. How many excess electrons does it have? We're going in the other direction. Given an amount of charge, can you determine how many electrons something has? Well, micro is the Greek prefix meaning 10 to the negative 6 or 1/1,000,000th. So it's your job to figure out how many electrons that is. Well, 20 microcoulombs times 6.4 times 10 to the 18th electrons per every coulomb, and there's 20 millionths of a coulomb there, says that's a whole lot of electrons. That's 1.25 times 10 to the 14 electrons, or 100,000 billion electrons. That's a lot of them. And that's not an unreasonable charge for a piece of confetti to have. The point is, electrons are very small and very mobile. That's why we discuss electrons being the charge-carrying particles. We don't discuss the motion of protons. They're not as mobile, but it's not particularly challenging to electrically charge a scrap of paper with hundreds of thousands of billions of electrons.
So let's suppose that a strip of paper has 6.8 times 10 to the 13th excess electrons. That means that many more electrons than protons. What is the charge on it? So if you know how many electrons you have, and you know the charge of a single electron, you could just multiply those two numbers together. So you would take 6.8 times 10 to the 13th excess electrons times the charge of a single electron, which is negative 1.6 times 10 to the negative 19th. That's coulombs per electron, to give you an answer of negative 1.1 times 10 to the negative 5th coulombs.
Which doesn't sound like a lot, but that's a lot of electrons.
It's a whole lot of electrons.
If charge can flow easily along the surface of a material, we say that that material is a conductor or that it is a conducting material, depending on whether we're talking about the object itself. We'd say it's a conductor. The material be a conducting material. For example, copper wires are good conductors. It says insulator. It should say conductors. That's That's on me. Copper is a conductor. Don't take a screenshot.
Copper is an excellent conductor. So the complete opposite of conductors, is an insulator. And in insulators, charge can't flow easily along the surface of that particular material. And as you see in the picture, rubber duckies are good insulators because they're made out of rubber. Other good insulators are glass. Glass is a good electrical insulator. It's actually what's used as a spacing material between power lines and wooden posts on the telephone poles that you see outside of your house. Yeah, there's plenty of other insulators, but what you need to know is that charge does not flow easily across an insulator.
Even if an insulator becomes charged. An insulator can be charged, but charge won't necessarily flow on it. And that's what happened in the previous example. If we applied an electric charge to paper somehow, the charge wouldn't move around very much. It would sort of stay right where we put it. So here is a conducting sphere that is initially neutral. You have many different options when it comes to representing electric charge or interpreting representations of electric charge. You'll notice I haven't drawn any charges on this. Likewise, I could draw a neutral conducting sphere like this with maybe the pinkish purplish spheres representing positive charge and the bluish spheres representing negative charge. There's a blue sphere for every pink sphere, so this sphere is still neutral. Realistically, this is maybe a better representation of a physical object. There are moles and moles and moles of atoms inside of something. So moles and moles and moles and moles of charges. But the total net charge, if you add up all the positives and you add up all the bajillions of negatives, well, the total is zero. That's what a neutral object means. So it's going to change from being a neutral sphere to a charged sphere. I drew some extra electrons in this next one. I've highlighted the extra ones in orange. This is also a good representation of a charged conducting sphere. It's a fairly accurate representation in that the sphere looks to be full of charge or pretty close, and that there are lots of positives and lots of negatives. The only downside of this representation that you see is that there's a lot of things to draw. So it's not a very practical representation. In your classes, your instructor or you may have drawn it this way at first and eventually gotten to the point where you feel comfortable just drawing the extra charge. I worked through that process with my students, and towards the end, we began only drawing the excess charge, not all the individual pluses and minuses. Just if there's a few more minuses, we just drew the few more minuses. And in our imaginations, we remember that there are many, many, many positives and an equal number of negatives that we have not drawn. Likewise, you may not have drawn circles or spheres, you may have drawn minus signs, another perfectly good interpretation, another perfectly good representation of a charged conducting sphere. Of course, electrons are mobile. A sea of electrons allows electrons to flow easily. Electrons aren't tightly bound to metallic bonds. Electrons, as we'll discuss in a future lesson, but I'm sure you remember, are negative, thus repelling each other. Electrons push each other away. So those electrons apply repulsive forces to each other. And they try to get as far apart as possible. Electrons spread out over the surface of a sphere. Charges spread out over the surface of a sphere. What that means is that the charge would be evenly distributed around a sphere and not in the middle, distributed around the edges. So we're going to bring in a second charged object. You see two charged objects on your screen right now. Charges want to spread out just as much as they can. So if these two charged objects are brought together, the charges want to spread out as much as possible. So both objects will become charged. And this is called charging by conduction. When two objects touch, if they are conductors, charge will conduct, will flow from one to the other because charges repel similar charges. But just like temperature and heat energy, energy doesn't flow by heating unless there's a temperature difference. For identical spheres and identical spheres only, don't take this as the rule. For identical spheres, charge will not flow unless there is a charge difference, unless there's a charge imbalance, if one sphere is more charged than the other. The details of that rule get a smidgen more complicated as we deal with materials that are not identical. We'll eventually revise the rule to say charge flows until there is equal potential. But right now, charge flows when there's a charge imbalance if the spheres are equal. Also notice we started with 4 negative charges and now it's split, 2 and 2. All right, so what if there were a third object, and that left sphere has a net charge of -8. I don't know the units, but it's -8 white dashes. What would the charge distribution be if we took the left sphere and the center sphere and touched them? Well, it needs to follow a couple of rules. 1, negative charges repel negative charges. And 2, charge is conserved. So an equal number of negative charges would spread out to both spheres. And finally, what if we then touched the last spheres together? Well, the same rules would apply, but as there's only half as much charge to spread out, each one only becomes half as charged.
Those are excellent examples of charging by conduction, but the second type that we're going to talk about today is polarization. So polarization is not the same as conduction at all. It's in fact when two objects are very close together, the charges in one of those objects affects the charges on the other object. And notice I said not even the same as conduction because they're not touching. They're only coming near each other to induce a charge on the other.
So here we have on the left an insulating sphere. The charges on that sphere are not going to move. They're not going to conduct. These two materials aren't even going to touch, but I drew an insulating sphere so you would know we're not looking for charge motion on the object on the left. When we bring these two objects close to each other, however, notice the negative charged insulating sphere repelled negative charges to the right side of your screen from the left side of the conducting sphere. Take just a moment to think about that. The charges, those negative charges on the right side of the shiny metal sphere, those negative charges got there because they were pushed away by the negative charges in the insulating sphere, leaving the left side of the shiny metal sphere positive. So that shiny metal sphere started off electrically neutral. Well, count the charges on it. I see 4 positives and 4 negatives. That sphere is still electrically neutral. We would say it is polarized and uncharged. Now, if we were to bring in a significantly larger sphere, a larger conducting sphere, maybe even one connected to the Earth or to the ground, that sphere would conduct over the charge just on one side of the smaller sphere, of that central sphere. So the larger sphere has negative charge on it. The central sphere is now charged net positive. If we were to then get rid of the larger sphere and get rid of the insulating sphere, now that central sphere, that conducting sphere, has positive charge on it, which spreads out evenly. So to back this up, at first, we induced charge polarization by holding a charged object near a neutral object. Then we grounded just one side of the polarized object, conducting away some of the charge. And then finally, after removing away the grounding object, we also removed the initially charged insulating sphere, leaving only behind a now charged conductor. So we've discussed charging by polarization. We've discussed charging by conduction. And we said that we would talk about charging by friction. Some of you may have seen this example before. This is an example from the University of Colorado. Thank you very much. This is the classic John Travoltage. Now, there's a few things you can do here. If you are an older brother or sister, you already know this process. You can scuff John Travolta's feet here along the carpet and have negative charges accumulate on the tip of his finger. And those negative charges, when there are enough of them, they will zap from his finger to this doorknob. But why does that happen? Well, John's shoe is experiencing friction with the fibers in that carpet. And some materials are very good at giving up their electrons, and some materials are really good at grabbing electrons. Whatever the materials are in John Travolta's shoe, they seem to be really good at grabbing electrons from this carpet. And as I grab some more, what I'd like you to realize is where the electrons are spreading out on him. Built into this simulation is the idea that electrons repel each other. Notice the electrons are concentrating along the edge of the figure. They are accumulating on the outside, not so much on the inside. And unless John's finger is close, those charges will not flow. In fact, if his finger is too far away, there's no flow. Sorry about your knee. And if his finger is close enough, there's lots and lots of flow. Okay, Mr. Eaton, I'm going to stop this share and hand it over to you, all right?
Sounds good. All right, give me just a second here.
Sure thing.
And share. Okay, so here's another example of charging by friction. And this time we're not dealing with static electricity, that electricity jumping from a fingertip over to a doorknob. But you may have actually done this in class. Hopefully you've had the chance to do this in class. But you've got a balloon and you have a wool sweater. And just like Mr. Mancina was saying, some objects are really good at grabbing electrons and some objects are really good at holding on to their electrons and or giving them up, so on and so forth. So if you've done this with a piece of wool and a balloon, if I go ahead and turn on charges, you'll notice that before we do this, the balloon has a net charge of 0. For every proton, there's an electron. So I see 4 electrons and 4 protons on the balloon. That's this guy right here. And on the sweater, each one of them has a proton that's paired up with an electron as well. So if you did this lab, this is essentially what you did. You took the balloon, and balloons are great at getting electrons off of other objects. Check that out. This is amazing, just amazing. So I can now take my balloon, which has a net charge of negative a whole bunch, and my wool sweater is now in a deficit of electrons. So it has a net positive charge of a whole bunch. I'm not going to take the time to count those. Feel free to screenshot it and count it later if you'd like. But if I take the balloon away from the sweater, notice that all the charges are still kind of hunkered down on one side of that balloon. And same for the sweater. You have all that positive charge that's built up on the right side of the sweater. If I take the balloon way over here and I release the balloon, what do you think is going to happen? Okay, it looks like we've got some nice little attraction going on. And that's specifically because the balloon is negative and the sweater is positively charged. All right, so let's reset balloon. And I'm going to add the wall. So there's this wall of unknown material, but I have a net 0 charge on the wall, net 0 charge on the balloon, and 0 charge on the sweater. Are there charges? Yes, but the charge is 0 on those. It's not negative something, it's not positive something, because there's a pair for every electron, there's a proton. All right, so I can do the same thing. I can take this balloon and, oh, that's interesting, nothing's happening. So in order to charge one of these objects, I know from my previous example that I can take this balloon and move it across the sweater, grab me some awesome electrons, and ooh, see what's happening with the wall. Why do you guys think that's happening? It looks like the balloon is a net negative charge. It has a whole bunch of electrons. I'm going to grab all the electrons off that sweater and take it back over to the wall. Now, the net negative charge on the balloon is causing a force to push the other electrons inside the wall to the right. And I can even move that balloon around to show you how much force that's causing between the electrons. You know that electrons repel other electrons, so they're really just trying to get as far away from each other as possible. But what do you hypothesize is going to happen if I release the balloon from this spot right here? The wall is still zero charge, but the sweater is a positive charge. So if I release the balloon, check it out. The balloon is attracted to the sweater again because of the opposite charges. All right, and Mr. Mancino, I think that's it for this particular simulation. I haven't found a use for two balloons.
That's all right.
I'm going to hand it back to you.
Thank you very much.
You're welcome. That's too much fun. I could just play with that all day.
So actually, before we do the guided practice, I think we have time for one more example of not John Travoltage. This is a device called an electroscope. You've probably seen one in your class before. Down here on the left. It's kind of a crude drawing, but it shows a flat piece of conducting material on top connected by a conducting metal rod to two very thin light pieces of metallic foil. And if you were to bring a positively charged a positively charged insulating rod, as you can see there, as I bring it closer to the electroscope, at some point, the top of the electroscope becomes negatively charged as electrons are attracted up towards the positively charged insulating rod. So the top of that electroscope becomes negative, and the bottom is now missing electrons. There are fewer electrons on the bottom than there used to be, so the bottom becomes positively charged. And since like charges repel, you can see that the leaves of that electroscope, that gold foil, has pushed itself away. I'm going to close that window and that one and stop one share, start up another. Okay, now we can talk about some guided practice.
All right, we're throwing you a curveball again. No 3 questions this time. We have 5 questions for you because there is a ton of content to cover in today's lessons. Even though you may have found it kind of simple, there's a lot of different questions that we need to be able to answer. So we've got 5 questions for you. The first, second, and third questions are about charging by induction in different scenarios. Of course, they're not all the same type of question. The fourth is about electroscopes, and the fifth is about conservation of charge.
One of the reasons that we're making sure that we've asked so many conceptual questions is because on the exam on May 13th, there are going to be a lot of why questions. I know that there's no multiple choice on the exam, but there's a lot of explaining why things happen. There's going to be less how much, how many, and when, and a lot of why and a lot of how.
All right, let's take a look at our first question. And just like Mr. Mancino said, we know there's no multiple choice, but we're trying to show you as many models and as many representations as you can possibly use to help yourself answer the questions that you'll see on the AP exam this year. So let's check out this problem. This one says that spheres A and B are identical in size. That's an important note because we do have a question about different sized ones. They're made from the same conducting material. Sphere A is attached to an insulating rod, and sphere B is suspended from an insulating thread. So the point of them stating that both of those objects are only touching an insulator is to show you that that object is not grounded. So sphere A initially has a charge of positive 10 nanocoulombs, and sphere B is initially uncharged. Which of the following best represents the distribution of charge on the surfaces of sphere A and B when they are brought near each other? So notice that they are not touching, so we're not going to be distributing charge between the two spheres. but there is going to be some sort of induction happening or polarization happening on one of the spheres. So if you start off with sphere A as being positively charged, if I look at my answer choices, I notice that every single one of those has a positive charge. However, notice the two left-hand representations where it says sphere A that are stacked on top of each other on the left-hand side of your screen. The positive charges are kind of moved way over to the right-hand side of the sphere. Then on the other two choices, we have our positive charges all on the left-hand side of the sphere for sphere A. So knowing that sphere A has a charge of positive 10 and B is initially uncharged, I need to look at my answer choices for sphere B real quick just to see what I might be able to rule out. Since I'm not charging by induction, there should be a net 0 charge on sphere B still. So if you look at sphere B, which one does not have a net 0 anymore? Looks like the bottom left-hand choice has more electrons than it does protons. So the bottom left-hand choice is not possible. So let's take a look a little bit further about, let's see, sphere A, sphere B. Okay, look at your bottom right-hand choice. What's wrong with that one? If you notice, sphere A has a net positive charge, so you know that electrons should be attracted to the left-hand side of sphere B. So that narrows my choices down to the top two choices. And which one of those do you think is going to be best? Well, you're right. It's the right-hand answer choice. My sphere B has my positive charges moved way out to the right-hand side. My negative charges are moved way out to the left hand because my negative charges are attracted to sphere A.
Click through this one. There we go. Had loaded up correctly. All right. Oh, no. There we go. Mr. Reed, take it away.
Oh, I'm sorry. I thought you were doing this one. Okay, so we have another setup that it looks like there's three different objects in this particular scenario. Now, students perform this experiment using the setup shown, and a sphere with uniform charge distribution is on an insulating stand. And again, that's to note that that object is not grounded. And it's placed a distance from a parallel uncharged conducting plate separated by a fixed distance d. So familiarize yourself with the diagram that you see really quick. It gives you points A and B that are labeled on the diagram. Which of the following best explains how and why the charges will distribute on the plates? So we know as we bring that positively charged sphere in closer to those plates, the negative charges in plate, let's call it plate B, it's the one on the right-hand side. The negative charges inside that B and inside of that plate will be attracted to the right-hand side of the plate, leaving a net positive charge on the left-hand side of plate B. So if I took a second to read through all these answer choices, I don't think we have time to read them all to you. But if I know that I have negative charges on the right of plate B and positive charges on the left of plate B, that only leaves one choice for plate A. And that means that negative charges will be on the right of plate A and positive charges on the left of plate A. So answer choice C, I think I said that one wrong. Answer choice C is the right answer for this one.
But one really important thing to notice is that at no point do plates A or B become actually charged. They remain electrically neutral. And that, as a student, that's one of the things that you need to notice, that even when charge polarization is induced, the net charge is still 0.
And part of that justification didn't have anything to do with the distance L or distance D. So that was kind of interesting.
Mm-hmm. So we have the balloon example facing a bit of a different way, and your job is simply to choose the representations that best model the behavior that's going on. Which of the following could model the excess charges in the balloon and the molecules near the surface of the wall when the balloon sticks to the wall? So let's take a look at what's wrong. If this balloon was charged and it was brought near the wall, what would things look like on the wall? How would the wall become polarized? What do you think? Well, in each case, I noticed that the polarization in the wall is arranged in a way that one side of the wall is positive and the other side of the one side of the surface molecules is positive, the other side is negative. But in the top right image, for example, the charges are on the wrong side of the balloon. That would not produce an attractive charge. If we take a look at the also the top left image, this was supposed to be a representation of the net charge on the balloon. If it's just looking at the net charge, we're not looking at the individual charges. And also the net charge on the balloon in the top left would be 0 anyway. We're told the balloon is charged. So the only places where we see a charged balloon in an orientation that would be attracted to the wall are the bottom two options. Oh, that clicked over. Student is charging a metal cup by attaching it to an uncharged, the cup is attached to an uncharged electroscope. A charged rod is lowered into the cup without touching the sides of the cup. And as a result, the leaves of the electroscope separate. This time, they repeat it and they ground the electroscope. And the ground is removed before the rod is removed. The leaves remain separated. What can we conclude about the charge on the separated leaves? So, to retell the story, it's always a challenging thing to read these. A charged rod is brought close and the leaves separate. But then a charged rod is brought close. Opposite charges are attracted to the top of the electroscope. A finger charges and then the charged rod is removed. That's right. The leaves are charged in each trial, we can tell, but in the second trial, because the leaves were grounded and became uncharged from the grounding rod, they have the opposite charge once that charge redistributes along the electroscope. That keeps filling the answer. So here are three conducting spheres, A, B, and C. Notice that C is smaller. So A and B are brought together, and then B and C are touched and separated. And your job is to determine the final charge on sphere C. We are a bit pressed for time. Nestled into this is the idea that once A and B touch, they will have equal amounts of charge, plus 3Q. But when B and C touch, because C is smaller, C will hold less charge to be at the same potential, a concept that we'll be discussing shortly. So even though B and C touch when B has a charge of plus 3Q, C will have a charge of less than 1.5Q. Okay, the key takeaways from today. Did you learn that electric charge was conserved? That charge can be transferred by conduction or induction? An object can become charged by induction. It can become polarized, grounded, and then charged. But during the actual process of charge polarization, nothing becomes charged. Charges can separate to opposite sides of an object, but when the charges are still on the object is uncharged. A neutral object can be attracted by a charged object.
And can you answer these questions? What is the purpose of grounding an electrical device? After walking across carpet, you reach for a door handle and receive a little bit of an electric shock. What types of charging were taking place during that process? And why does lightning strike? It's a broad question.
All right, so grab a couple of screenshots of these. Here's where we'll pick up tomorrow. A conducting disk is on top of an insulating stand. And students want to figure out what the charge on that disk is. They know it's charged, but they don't know whether it's positive or negative. They have a cloth that they know can give a plastic sphere a positive charge. They have a cloth that they know can give a sphere a negative charge. So what could they do to figure out whether the disk was positive or negative? Page 2 of this question involves some ideas from AP Physics 1 and some knowledge about Coulomb's law. So you're going to have to dig back into the Wayback Machine and see if you remember Coulomb's law. Grab a screenshot of that one. As those charged disks are brought closer together, there is eventually a point at which they start to, as disk 2 starts to move, as disk 1 is brought closer and closer. Finally, we discussed how graphing the experimental data to answer the question that was asked. So what would you graph and what evidence would you look for? Thank you very much for joining us as we introduce the concept of electrostatics. There are 3 more days of electrostatics in which we delve into electric forces and fields and potential energy and conservation of energy. So this is only day 1 of 4 for what is notoriously among the most challenging topics in AP Physics 2. So thanks for hanging in there. We'll see you tomorrow.